Okay, by now, I think you have learned more than 60% of the commonly used Verilog syntax. You can describe DFF and you can describe combination logic. So, in this section, I will show you how to use the Verilog knowledge you have learned to describe some small but useful circuit. Okay, let's have a quick review of the describe of sequential logic. Can you understand the meaning of this code? The first one, the second one. Can you understand the function of this code? And can you draw the circuit diagram for this code? Pay attention to the difference. Yeah, the difference in the sensitive list. So this may be the diagram for the first segment. This is a synchronous reset DFF. And this is a synchronous reset DFF. Yeah, please note the difference in the actual code and the circuit diagram. Usually, for a synchronous reset, there is a pin. Okay, there must be a pin at the DFF cell. And for synchronous reset, there may be a synchronous reset pin or may not. Okay. So if not, you can use the marks before the D pin to make the synchronous reset function. And usually, we prefer a synchronous reset in our design. Okay, so let's go on. The first is edge detect. So there is clock and D in input, and when there is a rising edge and D in, you can output a 1 cycle width path. You can say 1T path. So, how to design this circuit and write it in Verilog? For every rising edge and D in, you will output a 1T width path. Can you think out the Verilog code and the circuit diagram? Usually, you first think about the circuit diagram. Okay. So this is the answer from me. We have D and we have delay it for 1 cycle. Okay. So this at this point is a signal after delay. We use the DFF to delay the signal, to delay the D in for 1 cycle. Then we invert it and add them together to generate the pulse. Yes, at this point, D in is 1 and the delay signal is 0. Yes, add together, generate the pulse. So this is the circuit diagram. You first think about the circuit diagram, then you write the actual code. Then you can imagine the waveform. Yeah, the waveform of this function. Oh, sorry, the waveform is already here. Okay. Okay, you can simulate this code in Verilator and check whether the waveform is the same as this one. So there is a question for you: how to design a falling edge detector. That is every 48, yeah, such as, okay, you will give a pass here. You will generate a pass here. Okay, how to design a 40 edge detector? First, think about the block diagram, then write the actual code. Second is counter. Okay, counter, that is, for example, we have the 4-bit counter. It can count from to 15. Then it will loop back and count again. Yeah. And for this, we have an enable signal. It will control whether it will halt or it will count forward. So when en is 1, it will count forward. When en is 0, the counting will halt. So this is the actual code. Yeah, simple enough. And this is the waveform. You can see reset value 0, and when en is 1, count once, count once, count once. When en is 0, keep the last value. Okay. By the way, this is the waveform from model sim, not Verilator. Okay, you can try it in Verilator. It must generate the same waveform. So can you draw the block diagram for this circuit? Okay, I will give you my answer. Okay, something like that. When you do the circuit, for add some other functions, you can just draw it as a symbol. Okay, a symbol is okay. So there is one question for you. Question 1. Can you add an input signal called up down? Yes, you add an input here and its name is up down. Then it will control. Okay, then it will control the counting direction. Either it will count up or either it will count down. Can you do that? Yeah. For example, when up is 0, okay, it will count up. When up down is 1, it will count down. That is count down is it will count from 15. You can see, yeah. Yeah, this is countdown. Yes. So can you make this circuit? Or can you think how to write the Verilog code? Okay. And question 2. Add another 2 input signals, load and maximum count value. Then you can control the 2 input signals are used to control the upper value of the counter. For example, here, the upper value is default to, yeah, yes, the upper value is default to this value for our case. But can we control the max value? For example, we want to set the max value to 10, yeah. Any value less than 15. Yes. So can you make it? Okay. So this problem is a little difficult than the first one, and you need to think about how to describe this function in Verilog. How to describe this function? How many signals you need to have to describe this function? Okay. Okay, let me explain something here. Why this can count down? Oh, sorry. Why this can loop back? Such as if you count 14, 15, why it will loop to 0? Why? Do you know why? You can try it, okay? This is a 4-bit, yes, 4-bit, 1 and by 1. What's the effect? Yes, and we discard, yes, we discard the carry in, sorry, and we discard the carry out, so the 4-bit 0 is assigned to it, yes. So this will automatically loop back. And the second is, there is something new for you. Okay, we have declared the direction and the signal type along with the signal m in the round brackets. Okay, we have merged them in one place. Okay, this is also allowed in Verilog. Okay, you can merge them in one place. Okay, the next is shift register. It's something like that. You have many registers, such as there is 4 registers, and the value can be shifted. The value here, for example, the reset value for this or 0, then there is a 1 here. The value of 1 will be loaded here. Yes. Yes. And for next cycle, we assume the value has been changed to 0. So for next cycle, 0 will be loaded in here, and this value will be loaded to this point. Yes. So next cycle we assume the D in keeps 0. Okay. So this is 0. Yes, and the 0 value here will load to here, and the 1 value here will load to here, and the 0 value here will be loaded to, yeah, you can see the value is shift, yeah, at each cycle. So this is called the shift register. So we can shift value towards one direction. Okay, right or left is okay. This depends on the collection. Okay, on the collection of your circuit. So you can shift one direction, left, right, and there you can have some advanced features. For the example of this circuit, the shift step is only one register at each cycle. You can give the step of 2 or 3. Okay, that is the value here for a cycle. It can be shifted here, and here can be shifted to here. Yeah. Yes. Okay, you can try it. For example, if you set the shift step to register, okay, can you draw a diagram? Can you modify this diagram to this specification? Okay, and for the article code, the diagram I have shown in last slide. This is the block diagram, or you can say the circuit diagram. So this is the article code. Yeah, this is shift to higher bit. Okay. D in, the input value is at the least significant bit, and the value will shift towards the most significant bit. Yes. And this is the waveform. You can see the value and bit 0 will be shift to bit 3. Okay. In this format. Yes. Okay, please note that if you use Verilog to run the simulation, you can't see the unknown value here at the beginning of the simulation. Okay, this is because Verilog is a free tool. It's just a two-state. Yes, it's just a two-state value system. That is, it just has the value of 0 or 1 for each bit. It doesn't simulate the value of x or z. So you can see the x value here. But for other simulators such as ModelSim, VCS, they are 4-state value system. Okay. So can you think about the shift to lower bit function? Can you draw a block diagram for shift lower bit function and write the Verilog code for it? Okay, try it by yourself. I will give you my answer. This is the waveform for the shift to lower. You can see the MSB, the value on MSB will shift to LSB. Yes. Yes. So this is the code. The D and the MSB, and the value will be shift to LSB. And okay. Okay, let's say the bidirection shift. So for bidirection, you must have a signal that can control the direction. Yes. So you just combine the two functions here. And under the control of direction signal, you can have shift to lower bit or shift to higher bit. So you can see the diagram. Yes. Okay, the question for you is, can you draw a circuit diagram for this code? So remember, after this chapter, you need to have the ability of consistency between circuit diagram, actual code, and waveform. Yes, I expect, or I require you should have this ability. This will be a good start point for you to design complex circuit. The consistency means if given either one of them to you, you can figure out the other two. Okay, in the real application, you can have feedback paths. Okay, you can modify the shift architecture a little. For example, you can add some feedback paths and add some logic to calculate the new value for this register. Okay, you can have some modify on this simple shift. Okay, that's all for this section. Thanks for watching, and all this code, if you can understand, or if you think it's difficult for you to understand, you'd better write this simple code and simulate it in the Verilog. Check the waveform and draw the circuit diagram. This will help you understand the function of the circuit itself and the relationship between circuit, actual code, and waveform. Okay. Thanks for watching.